Summer's here, and so are our great last-minute getaways. Book a Jet2 holiday for this summer. From timeless Turkey to stunning Spain, you can now fly to over 60 destinations direct from Manchester Airport. There are loads of free Child Place holidays still available, and as always, you'll get 22 kilograms of baggage included. Jet2 Holidays. Package holidays you can trust. After protected. Subject to availability and conditions.
Calling all spinners. Join Sky Vegas, the online casino, where we offer new players 50 free spins to use in your first 7 days. And 200
or not. Okay. Hi everyone, it's Obi-Wan Piz for N-Simplex Pachinko. Sorry about last night and the night before. I caught something probably on the London trip and ended up, well, you can hear it. It's still not great. However, it is still much better than it was the last 2 nights. So, we're going to probably take it a little bit easy tonight. I don't know, we'll see how long it goes. And possibly at some point just bail and go play Elite Dangerous, because they've got some cool stuff going on in there. I am not getting the Type 11, which is the new mining ship. I haven't really done any mining at all. And there's still a community goal going on, so we'll see if things... yeah, we'll see if anything is going on for that. I think last time we did a... goodness. It's been a while. Last time we looked at one of the examples that was in here, but it did not actually include... we did a different implicit differentiation thing, and then we tried to find the second derivative of it, and it was like really bad because it's implicit differentiation. Second derivative is usually pretty bad. So if you can help it, you know, we tend to stay away from those, or do them in general, and or do as few quotient derivatives as we possibly can. So for that one, at least, the second derivative was not like awful, but at the same time, it was not something that I wanted to try to find zeros for, or try to find where it has particular critical points. So we kind of backed out of that. And then we found the second and maybe third derivative of natural log of x. And then we started talking about curve sketching. There we go. It's a wild spoonerism if I ever heard one. So anyway, we were talking about curve sketching. Ew. And we said that there are kind of 3 possibilities. Good evening, Zach. Catches me a little off guard. It's alright. So we do have f prime is less than 0 as an option. We had f prime is equal to 0 as an option. And f prime is greater than 0 as an option. We can do those in any order you want, naturally, but I'm just doing it in numerical order, since it's going from negatives to 0 to positives. Otherwise, we'd probably do like, what are the positives, then what are the negatives, then what's 0. Just because oftentimes that's how we think of like what numbers to use. Right, and f double prime is less than 0. F double prime is equal to 0. And f double prime is greater than 0. Now we said for the... Good evening, Sandra James. I do not have a specific Discord. However, we do have... Now that I'm thinking about it. Hang on. We'll just keep failing. If you go to Penn Center's channel, he's got his Discord link oppositionally? No. Alternatively, there we are. I can find it in like a minute or two. Oh, not that one. So The Elements is our Discord server that we typically use. Yep. That's it. Actually, I have a different invite link, interestingly enough. I'm sure it doesn't really matter where you come from, but nonetheless. Okay. So when we're talking about first derivative, typically we're talking about, and we already talked about this last week, but when we're talking first derivative, we're talking about slope. So here we see that the slope is negative, the slope is 0, the slope is positive. What's happening at each of those locations? Well, again, slope is negative. We have something that goes like this. Slope is 0. We have something that, roughly speaking, goes like this. And then slope is positive. We have something that roughly goes like this. Right? And then when we talk about second derivative is talking about curvature. So what is curvature? Well, it's the direction that whatever curve it is accelerating toward or curving toward. So here, when we see that f double prime is less than 0, we know that the negative curvature is going to do something like this. Something like this. A curvature being equal to 0 means that it is not curved, so it's going to be linear, some kind or another. And again, a curvature that is positive is going to have an upward acceleration. Lowercase kappa. Okay, so if we look at this and we say, what exactly is happening with all of these? We need to take these two things acting together and say, what do they do for all of it, right? And you know what? Putting it in the middle was a mistake. Maybe not. But whatever. Curvature, right? Negative curvature is going to be this way. no curvature is going to be linear of some kind or another, and then positive curvature is going to be curved upward like that. Okay. And again, negative slope, zero slope, positive slope. So what does that do for us? Well, something that is curved downward but always has a negative slope is going to look, roughly speaking, like this. And then we could extend that and say that, yeah, I mean, even if we went further in this direction, right, we could extend this indefinitely in this direction as long as its slope is, that's a positive slope. Interesting. Right, a negative slope looks like this, and if it's curved, now it's going to go down faster as we move to the right. I think I know what the problem was. I went like this with my hand, which is backward to you. Right, and then we go up like this, and again, it could flatten out-ish, just as long as the slope is technically a negative number for all of these things. Yes, this stage right-hand rule. Right, something that is sloped negative but always has a zero curvature is going to be a linear function with a negative slope. And then if we have a negative slope but a positive curvature, that means that it still has to go like this, but then if it has a positive curvature, it's accelerating upward, which means that as we move to the right, it gets less steep. So here, this is going to be more steep as we go to the left, and then less steep as we go to the right. Again, it can flatten out-ish as long as that slope is still technically a negative number. Okay, let's skip to the positive slope there. So again, same logic. The negative curvature, but a positive slope, means it has to go this way, but then it has a negative curvature, so it's accelerating downward. So here, our slope becomes a more and more positive number as time goes on. And as we reverse backward through time, or what have you, our slope becomes a more and more negative number. A zero curvature and a positive slope is just a straight line again. And then a positive slope with positive curvature is, well, technically it's the only one left, right? So here we go like this for positive slope, but then we say, as we go further, our slope should increase. And as we go backward this way, our slope should decrease, become less positive. Smaller positive number. Now we've reached the art part of mathematics, where you're going to look at these and say, okay, how can we graph it effectively? So the more information you get for a particular function, the more accurate your graph can end up being. Okay. Now what about this f prime is equal to 0? This is a place where it is flattened, but the curvature is still going to be either positive, negative, or 0. How exactly could we do that? Well, if we have a 0 slope with a 0 curvature, then this is going to be just a flat line, 0 slope. Right, so this is horizontal. If our curvature is negative, like the one above it, then this has to curve in the negative direction. But you'll note that here, f prime is not always going to be 0. Over here, we know it's a positive number, and over here, we know it's a negative that should resonate with something back in your pre-calc days. Right, we had what was called why, thank you for the follow. My name is Obi-Wan Pez. This is in Simplex Pachinko. Normally I'm a little higher pitched and less sniffly coffee, all that good stuff. Usually our only coffee is here. Today it's tea, because it's one of those nights. I spent the last 2 days off because I was not feeling good. So, so our intermediate value theorem. Right. Normally we do math on Mondays and Wednesdays, and on Sunday we have satisfactory at the moment. Tuesday we have 9 souls, and Friday we have against the storm. So twice a week, mathematics. Mondays are usually reserved for math education, or at least that's my plan from here on out. Mondays are reserved for math education. Wednesdays are reserved for calculation. So doing actual, how do we do math and all that stuff. If you have any particular questions, you can always ask. I don't care what day it is. You can go either to that Discord link that Zach posted, which should technically also be this one, which is The Elements. It is our math community Discord server. It's more than just me. Managed by Penn Center, who is also one of our friendly neighborhood math streamers. So you can go check them out, Penn Center. And E to the 2I Pi over there is Zach, also wonderful, awesome streamer. And we have Dawn, who is currently playing DayZ, and Dr. Gold, who is at Actual Education. We've got all these wonderful people. There are many more who also do math tutoring, math help, all that good stuff. And we can introduce you to them through that Discord link. So head on over there if you wish. So the intermediate value theorem, the idea here is that if we have strictly less than, we can actually say that it's not going to be the endpoints. Okay. If f is a continuous function on this interval a to b, such that f of a is above 0 and f of b is below 0, without loss of generality, meaning we could just switch the two, it doesn't matter, right? So f of a could be below and f of b could be above. Then there's going to be some value c on that interval a to b, such that f of c, the function value at that particular location, is equal to 0. So if we were to draw a little sketch, got A, F at A, and B, F at B. Right? As long as f is a continuous function, you must be able to draw somewhere on this function such that our function is going to cross through our x-axis. It has to be somewhere because, and again, you can move this anywhere you want along that slider. If it's a function, then it's not going to be at the endpoints, A or B, but it could be literally anywhere in between. Now, for a mathematician, this is not a caveat. This is just a clarifier, at least once. So it could be just like this really fast period sine wave that hops through the x-axis an infinite, or not infinite, but a near infinite number of times, right? What is near infinite? A very large but finite number of times. And that's perfectly fine. It's perfectly acceptable to have a billion zeros that this ends up going through. Perfectly acceptable. It is also perfectly acceptable that there's only one. But there must be at least one in order to get from the top area to the bottom area on a continuous function. If it's not continuous, all bets are off, right? It could do anything you want. It could do asymptotes. It could do jumps. It could do all sorts of whatever discontinuities and end up on the opposite side without ever having passed through the x-axis. But when we're dealing with continuous functions, we know for a fact that f prime, our derivative, is going to be continuous, or at least we have to check, right? Go through and make sure that it exists. If it has a value, f prime is equal to 0, then it must exist at that point. Our derivative must exist at that point. So, for this, we say, well, okay, we're only going to deal with this one point. F prime is equal to 0 here. Because all of the points before it on the left-hand side had a positive slope, and all the points after it on the right-hand side had a negative slope. So you can keep working this back in both directions until we fall into exactly finding our C value, that special one right there, whatever that might be, where the derivative is equal to 0. Again, the curvature is really looking at what's the general trend of this thing, what's happening within this region. So the region is accelerating downward, so that's why it's slope negative, or sorry, why it has a second derivative that is negative. All right, and similarly, well, we could do the exact same thing over here. If we have a positive curvature, it must be curved up from flat, right? Flat has a 0 curvature. Curving downward like that has a negative curvature, so curving like this must be upward, positive curvature. All right, and again, we could do the same thing. Everywhere on the right-hand side has a positive slope. Everywhere on the left-hand side has a negative slope. This point right here on that vertex is the only place where there is a negative slope. Man, cough medicine must be like getting to me. I didn't even take any. This is the only place where the curvature is positive, but the slope is 0. There we go. You sure you guys want to follow? I'll be better next week, I promise. Yeah. Okay. So then, these are going to be, again, kind of general trends and patterns to watch out for. So if we can find a place such that the slope is 0, these become rather interesting, because now we can deal with them in sort of a linear fashion. So, first place is obviously the middle one. In the middle square, if our curvature is 0 and our slope is 0, then we just get this horizontal line. Nothing really terribly interesting about it. However, we also get horizontal lines when f prime is 0 and our curvature is not. So it's either positive or negatively curved. That also allows us to find individual locations on curvatures, on curved surfaces, where we have a flat spot. I don't know if you could quite see it yet, why that is super, super important. It is part of today's title, so the stream title, probably down there somewhere, right at the end says min-maxing. Right, now that is a D&D term referring to completely dumping one of your stats in order to boost all the others, or one particular one. However, it is the case in mathematics. We're looking for finding, as you see on these two examples with green dots on them, a minimum point and a maximum point. So in both of those cases, we have a single point where this function, the original f, is either at a maximum or at a minimum. Now that's really cool. Right, look for where f prime is equal to 0. And you can then tell which is going to be a minimum, which is going to be a maximum. By either, and there's kind of two ways to do this. Well, there's several ways to do it. Hey, Fizzbuzz. How are we all doing this evening? So, you could always look at it graphically. Right? Just look at it, right? Did it reach a maximum or did it reach a minimum? There you go. Okay, if you don't have a graph for it, maybe we are, like we're about to do here, going to make our own graph, right? You can't just immediately say, I know which one it is. Maybe you haven't graphed it yet. Or maybe you need to prove that it is what you say it is. So, one is by looking at the local values. So look at the individual points which are immediately surrounding the min or max, the extremum that you've just found. We also call them critical points. Critical points is often a way to not categorize it. Extremum. I won't go there. So if both are higher, then we end up with right? If both things are higher locally, so you have to specifically look in the immediate surrounding area. If both of them are higher, this point is a minimum. If both of them are lower, this is a maximum, right? It's going to have this maximal value. On either side, it's going to shrink away from that particular point. Right? And if it's one of each, it's neither. So in the case of one of each, it could be something like our cubic function, like this. We have y equals x squared, or y equals x cubed is going to get us y prime is equal to 3x squared. So that's going to get us a 0 value directly at x equals 0, which means that x equals 0 is a critical point of this and every other parent polynomial function. Very helpful. But when we look at it, you could see quite clearly this is neither a minimum nor a maximum. According to the stuff on the left, it's leading up to this point, so all points are lower, therefore it's a maximum relative to the stuff in the negative direction. But it's also a minimum if we look at all the stuff coming from the positive direction. Everything is higher than it. Well, it doesn't really help now, does it? Because what we're really doing is we're looking immediately surrounding this thing, what is happening. So you have to be able to draw kind of a circle around all of it, or there exists a circle that you could draw such that this is either the lowest point or the highest point, to call it either a minimum or a maximum, respectively. Right? Now, it is important that if you do this, you need to pick values that are locally close. So it has to be closer than the next critical point, which, I mean, shouldn't be that bad. If you're picking stuff that's like way out somewhere else, you know, that you might have a problem there. Okay, now right? Local slopes is another way to go about this. If you're going from a negative slope to a positive slope, then quite clearly you got something that looks, roughly speaking, like this. So, okay, that's going to get us minimum. If we have something that's a positive slope to a negative slope, then again here, you're going to have a maximum. I spent way too long on that. Okay. As a consequence, it was not very good. Okay, so you got the minimum at the bottom, the maximum at the top. They have negative slopes to positive slopes for a minimum, positive slopes to negative slopes for a maximum. And again, if they're the same, so here positive to positive is just like a cubic function. And negative to negative is also just like a cubic function, but going the other way. And that's not quite right, but close. And again, that has neither a maximum nor a minimum. All right, another way we could do this. Right, double check by curvature. In fact, we just did it up there. Right, so we've got f prime and f double prime. That's not what I wanted. Oh wait, f prime 0. Never mind. Oi. Right, so if your f double prime is positive, then we're only ever going to have at f prime being 0, that's going to be a minimum. And with f double prime being negative, this can only be a maximum. So just double check, make sure you got everything you need right there. Right, so quick reference table. So you could double check using the curvature, which is often what I end up doing anyway. because I want to do this with as little notation as possible, with as much explanation as possible. So I don't want to make this, and I don't even know. I don't want to make it like overly encroaching on how much time, effort, and energy it takes to do all this stuff. So, for instance, oh, right. We'll come back. Sketch y equals x squared times the quantity x minus 2 parentheses squared. So when we sketch this, like the entire idea is that you should be able to do this without looking at a calculator. We'll use the calculator at the end to double check to make sure that we do in fact have the right function and that it looks at least reasonable. It doesn't have to look perfect. So y prime here, we are finding that this is going to be, this is a product between those two terms, an x squared term and an x minus 2 squared term. So, product rule, like we did in previous weeks, I'm going to take the derivative of the first part, which is now the derivative of x squared is 2x. We're going to then multiply it by the rest of it, so x minus 2 squared plus x squared times, and now we take the derivative of the rest of the other side, which is x minus 2 times 2 raised to the first power, just like x was raised to the first power here. And then we take the derivative of the inside. So the derivative of x minus 2 is going to be 1, just like back here, the derivative of x was 1. If you want, we could also do this in generalized form, where this would end up being dx, like 2x dx, but then the other side would just be dy. Right, we would get this, and then we would factor out the dx and then throw it on the other side anyway. So I'm okay with, I'm okay with not worrying so much about the individual differentials and about taking it in general form. It's good for algebra, for like practice, but yeah, that's about it. At least at the moment. It's really nice when you're starting to do like Calc 3 stuff and you've got all sorts of letters belonging to different kinds of derivatives and all sorts. So, y prime is equal to, here we get 2x times x minus 2 parentheses squared, plus here we now get a 2x squared times x minus 2. For this, we want to then say, what can we factor out from all of this stuff? So I've got a 2, I've got an x, and I've got an x minus 2 common to every term. Then we would be left with an x minus 2 plus x. Just want to make sure. Okay. which is, if we shorten it, oop, not that, is equal to 2x times, this is now 2x minus 2, which I can take out another 2 and leave behind x minus 1, x minus 2. Flipping some stuff around, this is now going to be y prime is equal to 4x, x minus 1, x minus 2. Now, there's kind of two ways to go with this, right? We can, first off, take the second derivative. So, we didn't really talk about the larger product rules, but honestly, it doesn't warrant a whole lot of discussion. Right? Because here, if we've got 3 functions, oh no, we didn't talk about that. Okay. Associate the first 2. So then we take f times g parentheses prime times h plus f times g times h prime. Okay, what's f times g prime? Oh, that's another product rule. So that's going to be f prime g times h plus f times g prime times h plus f times g times h prime. So if you look at it, all we're doing, and this is true no matter how many terms you have that are all being multiplied together as one single product rule, all it is take each derivative in succession and add them all together. That's it. Nothing special. So in this case, right, we consider 4x to be the first term, so that's just 4 times x minus 1 times x minus 2. Again, times 1, because that's the derivative of x. Or, right, 4x, derivative is just 4. It's your choice. Add 4x times the derivative of x minus 1 is just 1. So, that's gone. X minus 2. Plus 4x times x minus 1 times the derivative of x minus 2, which is again 1. And as much as we can, we try to take out any terms which are common. At this point, all I've got is a 4. We could, in theory, right, expand everything out, recombine. And actually, maybe that's not a terrible idea in this particular case. So 4 times the quantity here would be like x squared minus 3x plus 2 plus x squared minus 2x plus x squared minus x. Okay, so then we got 3x squared minus 5 minus 6x plus 2. Right? And then we look at that and say, oh, look, it's a quadratic. Is that easily factorable? So this is going to be product of 2 numbers is going to get us 6. So 1 and 6, 2 and 3. Which of these pairs will add up to 6? Yep, we don't have one. So it is not easily going to be factorable. Why would you want to factor it, Obi? That doesn't make any sense. Sure it does. Because what we're doing at this point is we're saying, I would like this to end up being equal to 0. to find out where the critical points are. To find out where the critical points are for each of these functions. So for y prime, we go over here, 0 equals 4x times x minus 1 times x minus 2. Hey, that's super easy to find the zeros because it's all product. Right? Zero product property tells us that either x needs to be 0 or x needs to be 1 or x needs to be 2. That's it. And down here, 0 equals 4 times the quantity, 3x squared minus 6x plus 2. We're either going to need x to be, well, x needs to be one of the zeros of that polynomial. It's a quadratic. We can use the quadratic formula to solve that because we can't find a nicely factorable value. It's a shame, really. Right? There are no rational numbers, which are going to be zeros here. Divide both sides by 4. 3x squared minus 6x plus 2. We could do complete the square. It's actually not that bad, but anyway. Not the point. What we can do here is, again, look for x equals negative 6 plus or minus square root of negative 6 parentheses squared minus 4. A is 3, C is 2, all over 2A is 3. So x is equal to, this is going to be 6 plus or minus square root of 36 minus, this is 1224, which is going to be 12. Square root of 12 is not rational, but it is at least nice-ish, all over 6. Six plus or minus square root of 12, which again can break into 4 and 3. 4 is a perfect square. Hooray. And we could leave it like 2 by 3 when we do all this stuff, because that does mean that this 4, when it comes out, is going to be a 2, and we could factor it all from everything. So 2 divided by 2 is just going to get us 1. And then multiply by 3 plus or minus the square root of 3 all over 3. Okay. So, what we have is a function. Both terms in the original function were squared. So that means that we can only get non-negative values out of it. So we could get 0, we can get positives, but we're never going to end up with a negative number coming out. Okay, so what does that mean? Well, x is equal to 0 is going to be a point where we have a, that's not, nope, hang on. That's not a 0 of the original function. Hang on. We also need the zeros of the original function. Also important. Right, so y equals 0 equals x squared times x minus 2 parentheses squared when x squared is equal to 0 and parentheses x minus 2 squared is equal to 0. Now in both of these cases, we're looking at what is the absolute value of x equal to 0 and what is the absolute value of x minus 2 equal to 0. We could throw out the extra cases, right? So there is no positive and negative here. There is no possibility for 0 to be anything other than 0. There is no negative 0. Or rather, negative 0 is itself. So x is equal to 0 and x minus 2 is equal to 0. So x is equal to 2. Alright, so this is y equals 0 when x is equal to 0 or x is equal to 2. So actually we do have a point at the origin. Awesome. And then we had a point at 2. X equals 2, y equals 0, which is also going to be, let's put it in the middle, where this is also going to be at 0. Okay. Then we also found that x equals 1 is going to have a critical point. We also know that this is a polynomial, therefore it is continuous forever. So, now we can look at this and we say, now we need some more information about everything else. So, if we've got 0, 1, and 2, where we have 0 values, then we need to figure out what's going on in between and outside of these things. So we need test values. And if we're careful about how we pick things, we can also use the exact same test values for the second derivative. Although second derivative, we could also just use 0, 1, and 2 potentially. So kind of depends on how everything's working. So here we just want like a half, 3 halves, and 3. And then here we could just do -1. So what's going on with the derivative at each of these values? Like we could go ahead and get the original function and plug in all of these things to just get values, but quite honestly, it doesn't matter. I'm much more interested in determining the behavior overall than I am in getting every individual point. If we're doing that, we might as well just get literally every point on a table and then just graph it that way. You were doing that in Algebra 1. We want to know how to do this the calculus way. So in the calculus way, we're saying, okay, what is the derivative function at -1? And I'll tell you what, we don't even necessarily have to have a value. Let's just get a sign. So, y prime at -1. This is going to be negative, and negative, and negative. So overall, this is going to end up being a negative value. A half. Right? Oops. Smooth. At a half, we end up getting a positive number on the outside, a negative number on the inside, and a negative number on the inside for both of those. So a half is not big enough to cross any of these boundaries except the first one, where we went from -1 to a half. This is just x, so naturally makes sense. This is a positive times 2 negatives, gets you a positive. Adds are about to start. Same thing goes for 3 halves. The only difference is it crosses this one. So now this is going to get us a negative, and then 3 is going to get us all positives. We'll come back with a conclusion of that after ad break. Thanks everybody for sticking around. We'll be back. Since we didn't do our Tai Chi Cat yesterday, or Tuesday, wow. I've been sick for that long. On Tuesday, I'm thinking about streaming at 9 o'clock p.m. And here I am at 7:30 laying on the couch, already pretty much asleep. So I was like, all right, I'm going to bed. So I slept from like almost 7:30 at night until 10:30 when my spouse comes upstairs, tells me, hey, so you're saying you're like feeling feverish, why don't you take some ibuprofen? So I'm like, it's all the way downstairs. So I go downstairs, change the laundry, get the ibuprofen, come back upstairs, wake up at 1 completely soaked. I'm like, okay, well. And it's only been at night that the fever comes. So I think I'm better today in terms of like having a fever, because it's not, I don't feel the same. I don't feel like I'm having another one. But the throat is not happy. And the lungs, I suppose. The lungs. What are we doing? Not that one. That's different. There we go. So when we do Tai Chi type warm-ups like this, mostly what we're looking for is, again, to try and let the arms swing as freely as possible with gravity, and just kind of guide them into place without doing a whole lot of work. And then use knees to push as though you are giving them a little bit of gravity assist, like when you go on a swing set, something like that. Also, if you want the one in the front, you can get a little bit more power. You do kind of lean into it just a little tiny bit, not a lot. It's probably not even noticeable when I do it properly, but of course that is the key. You don't want to give it away, because ideally, when we do the type of Tai Chi stuff with me and my instructor, and possibly we're going to start joining up with another class, might be on Saturday mornings. We'll see how it goes. But the idea is that you want to use this kind of gravity assist and whipping action as much as you can so that you don't muscle everything. So one way to do this, again, for example, is if we're coming back for like a parry, you can kind of go like this, and it slaps whatever is coming at us out of the way. This way is a little bit harder just because it's already out here already. But you can kind of like twist a little bit, and it adds a little bit extra power. But similar to that also are the strikes, which go the other way. So we can start out here, and then just by shifting the hips a little bit, and not adding a huge amount of muscle power, we're just using essentially letting the body create kind of a ripple effect that goes up through it. And this is what some practitioners will call chi or ki, where you're effectively taking, some sort of magical energy and then channeling it through your body to then pop out at people and make them do silly things. Or get hurt, I suppose. I can quite definitively say that that's not really what's going on. And most of the time, when students do silly things, and this includes, I've seen multiple where like students will jump around like they're on fire. It's mostly because they've essentially become hypnotized to, or conditioned to just do that. These masters kind of, don't sue me. Many of these masters, I'm not going to call any of them out, you'll see them, kind of delude themselves into believing that they have these magical powers because their students do these things. And then when they fight like MMA fighters and karate practitioners and people who don't believe in their, there was a good term for it, bullshido. people who don't believe in their particular kind of bullshido, it doesn't work because their opponent doesn't believe it's going to work. And if that's your game, then what are you doing? But anyway, it's the same kind of stuff where like the chi energy really is this feeling that goes through your body. It's a ripple of energy, of power that comes from within, but not magical. It's just basically like taking a whip and going like that. You can put a whole lot of energy into the tip of the whip at the very, very end of its travel by just putting a little tiny bit of energy into the handle part of it at the beginning of its journey. So the same thing happens with your body when you're doing martial arts. Basically, if you can harness this ripple effect, then it can multiply your power by quite a lot. So sometimes you can just, like, you end up using this rocking energy, or if we go back and forth like this, what I'm doing is I'm creating a spring with my back leg, and again, I can use that at any point to advance, to retreat, to go into a kick, to do whatever I feel like. So there's several different things. We could do kind of like a push, like we've done in many other times, where if we're gripping the floor, we get knocked onto our back leg just a little bit by something that's coming usually either diagonally or usually by something that's coming at us, but at the same time we don't want to absorb all of this energy because that's going to get us off balance and then we're going to fall or something. But oftentimes if we absorb the momentum of a strike, we can then also return that on the sprung leg. And then, again, use that ripple effect to do a much more powerful push. And if you end up using the heels of your palms and they're aimed toward the floating ribs, it can be absolutely devastating. Although, to be fair, usually you want to be touching the ground when all of that happens. So I believe I may not have been actually. But anyway, yeah, so we have this here, and then you spring forward, and when you hit here, you relock, and then thrust all of that energy forward. All right, anyway, let's do a form. The only one I know, as we've determined, because I don't remember what the other one actually is. All right. Didn't go back. Alright, so we do the... So typically when we do the split elbow, here what we want to do is come back, not that far, come back on our back leg, and then spring forward for the shoulder. Then from here, this is where we go immediately back into this thing. Man, I am forgetting words today. Brain power is being all eaten up by, like, healing myself or something. Anyway, roll back. Press, push, pluck, split, elbow, shoulder. Anyway, that's probably enough for tonight. Okay, so we discussed before what all of these slope values were going to be. Again, whether they were positive or negative is really the only thing we cared about. So between, well, no, anything after 2 is going to be positive. Between 1 and 2 is going to be negative. Between 0 and 1 is going to be positive, and anything negative will be negative. Will have a negative slope. Got to be careful how I say that. So this means, right, again, we could go multiple different ways with this. Or we could say, okay, so I know that everything in this function prior to 0 needs to have a negative slope. So it must go like this. And then it's got to flatten out because this is 0. So presumably all this stuff is going to be more and more and more negative as we go further that way. Then it gets to be positive, so it's going to go up in here. And then, here's the thing, right? It's got to be 0 again at 1. So it's got to slow down until we hit 1, at which point it becomes negative again, so it goes down this way, and it has to reach 0 here. And then it has to have a positive slope all over this way. Now, if anybody knows from pre-calc how exactly all this stuff works, yeah, this looks reasonable. It's a polynomial. It is a 4th degree polynomial, which is what y is. It has 2 squared terms, so it has this nice little symmetry that kind of looks quadratic, but not really. And its zeros are 0 and 2, which have multiplicities 2. So far, all of this seems to check out. The only thing that we just want to check here is what's going on with f double prime. What is the curvature of this thing like, and where, if anywhere, does it change? So here's where this comes in. We know what the double prime zeros are, right? It was these nasty numbers, the 3 plus or minus the square root of 3 all over 3. So this is going to be 3 minus the square root of 3 all over 3. And this is going to be 3 plus the square root of 3 over 3. Where are these numbers? Well, root 3 is 1 point, right? It's got to be over 1.5. It's about 1.86, give or take. All right, let's not even worry about the estimation too much. I do know that a number that is higher than this is going to be well, I mean, even just the number 2 is going to be higher than this, because in order to be 2, you'd have to have a 3 plus 3 over 3, right? But this is 3 plus the square root of 3, so that's smaller, so therefore this has to be smaller than 2. 3 minus the square root of 3 is not negative. So I know that 0 is over here. We're okay with that. And then 1 should be in between, because that would be, what if the root 3 were replaced with 0 instead? So 3 over 3 would be 1. And in fact, it's directly between. Right, so 1 is directly in between these two things. So now I'm actually asking for, what are the curvatures at these individual points? So we've got this quadratic here. Even with the 4, right? Again, we only really care about what's happening to the sign of SIGN of y double prime. So the 4 doesn't really matter in all this. It's fine. Okay, what about 0? Well, that's going to get us 0 plus 2, which is going to be 8. So this is greater than 0. Y double prime is 4 times. What about at 1? Okay, so that's going to be 3 times 1 minus 6 times 1 plus 2, which is going to end up being minus 3 plus 2 is a negative 1 times 4 is negative 4, which is less than 0. And then y double prime, 4 times quantity. What if this was 2? So 2 squared is 4 times 3 is going to be 12, minus 6 times 2 is 12, plus 2. Okay, well, these are going to be 0. So now that's also 8, which is greater than 0. Okay, so now we know that this is going to be a positive, a negative, and a positive. No, hang on. Psst, don't do that. Sorry, at these numbers, 0, 1, and 2. Our f double prime will be positive, then negative, then positive at those numbers. And we know that the zeros are 3 plus or minus the square root of 3 all over 3, which can sum up to, where's my calculator? Alright. So 0.42 is right about here, and 1.577 is like right about here. I didn't draw well, but nonetheless. This should in fact be symmetric. So it's a product of me not drawing correctly. And again, we could take these values, if we wanted to, and plug them back into the original function and figure out what the values are, especially since we've got stuff like, y equals menu and function notation in the calculator. So we could just throw stuff in and we'll get all sorts of good answers out of this. Vars, y vars function, y1 of parentheses 3 minus root 3 over 3. Whew. All right. That one is 3 minus root 3 all over 3, comma, 4/9. All right, so 3 plus root 3 all over 3 should also be 4/9. And again, it makes sense because it's symmetric. Yes, that is true. And it's also going to be interesting if anybody is interested in doing it, why it is that a number that isn't just a positive or a negative of the same number is coming up with this stuff. So we're getting that this is a irrational conjugate. Why is an irrational conjugate, which is not just this number and this number negative, coming up with the same value when the original problem had squares in it? Right? It would make much more sense if we were like, oh, well, if we just squared that number, then the negative drops off of it. So, interesting thing to look into if you're into that sort of thing. Do an exploration. Woo! Okay, so those are where we have zero curvature. Now, zero curvature, we saw over here, is when we have f double prime equal to 0, but we just wrote straight lines. So, like, what's going on there? As it turns out, this is using the same reasoning that we did, for the first derivative, is that if we have a section that has a positive value and a section that has a negative value, then there must also be at least one point in between which has a 0 value. Since this is a continuous function and we found all of the zeros down there, right, we can say that it's, okay, it has to be one of these. Yeah, maybe not the best explanation for that one, but it's all right. It's kind of circular reasoning. Anyway. Yeah. Okay. No. That works. We found the only zeros by doing the algebra. So, therefore, there cannot be more zeros to our f double prime or our f prime or our f. Right? We found all possible zeros. And yeah, that's a y. Whatever, it's fine. Right, so here we go from a positive f double prime to a 0 f double prime to a negative f double prime. So therefore here we're going from a curvature up to curvature down. This point right here, and also the other one, are what are called inflection points. This is the location where the curvature changes, the location where the acceleration changes. Let's not do acceleration right now. Where the curvature changes sign. Right, we already know it's 0 because it says so up there. All right, so classically, right, these look like this has a positive curvature, and then the inflection point, and then this has a negative curvature. So you should be able to see this on functions from here on out, to look at this and go, ah, yes, I have recognized this point. Let me go see if I can find it. And look at a graph and just be like, the inflection point should be somewhere around here. Right? I don't know exactly where necessarily, but like somewhere in this little circle that I'm going to draw. Right? With me drawing the way that I did here, I was like, okay, it's going to be here. And over here, remember, it was like down there instead. It happens. Yeah, the distances are also different. So that's fun. All right, and then also on this side, we're going from a negative curvature to a positive curvature. Some people prefer to use the terminology concave up and concave down. So we're looking at the concavity of this particular function. I prefer curvature because it just goes with a lot of other topics that we cover later on. So. Okay. So that's what this function looks like. Yes, we should probably get actual values. So for 1, 1's going to be an easy number to get. 1 squared is 1. And this is x minus 2, so 1 minus 2 is negative 1 squared, also 1. So that's just 1. Right, this point here is 1, 1. I should not do it in that color. That's all right. And if it's something easy like that, right, no worries. It's pretty simple. Then we can just double check. I don't want the 3D version. So x squared times x minus 2 squared. Okay, so 0, 0, 1, 1, 2, 0. You can see that it has the classic W shape. And then we also have around here, right, an inflection point whereby we're going to get a change in the upward curvature to a downward curvature. And then again over here where we get a downward curvature changing to an upward curvature. Again, where exactly it is, you're not going to have the exact number showing up on the graph most of the time, especially if it's an irrational number. However, we do have points. So we can go with 3 minus square root 3 all over 3, comma, 4 ninths, and 3, nice, it works, 3 plus square root of 3 all over 3. Right, so when we put them on the graph, with all these other points. Right, now we have actual locations that we can fit in and see, like, okay, yeah, that's where our curvature changes. Here we have concave down, here we have concave up. It's kind of hard to see it exactly, right? Especially when we start zooming in. Can't really see it here. However, if we zoom out just in the x-axis, it becomes much more exaggerated. So here, 0, 2, 1. Nah, it might still be a little hard to see. But here, this is concave up. Here, this is concave down. Did I mean to do it the other way? Quite possibly. Right. 0, 2, 2. Nope. Okay. I thought I was being clever. That's part of the problem. 7. Yeah, there we go. I mean, this is just a matter of basically zooming out, so it's not really all that helpful. Right. You could see it to either side, but you can't really see what's going on right there at that point. Yeah. Anyway. So that's how we're going to work on using curvature to help graph functions. If anybody does want to see any further ones, we definitely can do that. But for now... So to remind ourselves from earlier, in order to be differentiable, we needed a function to be continuous. On differentiable on, I think, open. No, doesn't need to be closed. We could have that be open as well. And the definition of derivative Must exist for all. I think usually this is done with A because we want to say, like, you know, at specific values. For all A. No, don't do A. Bad habits. C on AB. Right. Never know if somebody's gonna bust in here. Alright, well, anyway. Okay, so... next thing we're doing is called Rolle's theorem. Named after Michel Rolle. Alright, who developed Rolle's theorem around 1691, so he was 39-ish, just in time for a Fields Medal. And he lived to age of 67, where he died in Paris. In a criticism of infinitesimal calculus, Rolle presented a series of papers at the French Academy alleging that the use of methods of infinitesimal calculus leads to errors. Specifically, he presented an explicit algebraic curve and alleged that some of its local minima are missed when one applies the methods of infinitesimal calculus. Pierre Varignon responded by pointing out that Rolle had misrepresented the curve and the alleged local minima are in fact singular points with a vertical tangent. Yeah, well, can't win them all. Clicked on differentiability. I forgot. There's also differentiability in higher dimensions and complex analysis. Woohoo! Anyway. All right, without loss of generality, you know how the thing works. So Rolle said that if f is continuous, on, well, okay, he used a closed interval, is continuous on closed A to B. Well, it makes sense because we're drawing them from A to B. With f at A equaling f at B. And f is differentiable on A to B open. Then there exists, again, at least one point, some C within A to be open, such that f prime at C must be equal to 0. Makes easy enough sense, honestly, but proving it is a tricky bit. I'm not going to do that. But it is proven using mathematical induction. You can show that at every individual point, you can look at it and say, okay, based on all the previous points, up to this point, we've had a value which is, I don't even know exactly how he goes about it, but we've had a value that is, lower than this. So if we continue upward forever, naturally, we're never going to get back to where we started. So now we have to add in some amount that's going to be negative, which means that because we had a positive slope and a negative slope in front of us, then we're going to have a slope with 0 at some point. But yeah, go ahead. Try and draw a continuous function that goes from A to B with f at A and f at B being equal. It's better. F at A and f at B being equal, and try to draw something that doesn't have a 0 slope. Like, obviously, it's going to have to happen. It's been proven. But also, right, it becomes a little more obvious when you just try to do it. Okay, if I go up, then I need to come back down again. If I go down, then I need to come back up again. So yeah. Easily enough, it could just be 1. So we could draw a just standard parabola, as if I were throwing an object from one place to another of equal height. It's going to just have this upward arc, and then it's going to reach a maximum, then it's going to come back down. Okay, this is intuitive enough. But then, Brooke Taylor comes around. At least I think it's the same guy. Oh, no. Much earlier than that. I lied. Taylor does some awesome things. We'll talk about him later. Lagrange. Joseph Louis. Hope that's his name. So I believe Lagrange is like the first one to state that it should be the case but it looks like he didn't actually prove it. Helpful. It's great. I love these things. So wonderful. No, boo. Don't want you to store anything on my device. There's no reject all for this thing. This is a UK thing. Every single website now needs to have these, like, by law. Okay, so I have on one site that it is actually Lagrange's theorem. Anyway, so Joseph Louis Lagrange comes around, obviously French, sees Michel Roll's theorem, also French, and says, tell you what, I can do you one better. If we have a different function, which is like pretty much the same as the one you picked, however, come on. You want to do this to me like every time. Arg. Boo. I swear, every time that I grab this thing, it would just automatically rotate it, and I'd be like, nope. But now it doesn't want... There we go. Okay, never mind. Lagrange said, you know what? Just spin this thing around. Right? Angle it. Take any function you want, and instead rotate it like this. And now we can get the exact same thing as what you just said, where all of these end up at these individual points. But right, as long as it is continuous and differentiable, just the same as the other one up there was, then here what we can do is we can find a particular value that goes through our two endpoints such that the slope that's found here is going to match the slope that's found at least one other point somewhere along this curve. I mean, absolute genius. Wonderful moment. So there exists some f prime at c such that the slope of the average slope, f of b minus f of a over b minus a, is going to be equal to that same slope at those individual points, at any of the following. There must at least be one. Okay, so here, again, if f is continuous on, again, same closed a to b, and differentiable on the open interval, then there exists some c in a to b such that AO. I apparently neglected the ads and they decided to run on me anyway. Shocking. Alright, we got a 3-minute break.
Chase is the digital bank you can rely on, with helpful 24/7 customer service.
So I can speak to a real person anytime?
Of course, even when you're on holiday and it's the middle of the night back home. And 100% cash back on everyday transport.
Like on the train to visit family this summer?
Roger that. Join millions of customers and see what your money can do with Chase. Search Chase Bank. 18 plus UK residents. Eligibility applies. 1% cash back on debit card spending on groceries, everyday transport and fuel for your first year. Max £15. Restrictions apply.
Paddy Power Games gives you more chances to win. Imagine that. Life with more chances. Attention people, I've a bold idea for men's hairstyling. Bringing back that 70s classic. Security. At Paddy Power Games, we believe in giving you more chances with free spins, cash and free on Paddy's Wonder Wheel. More chances to win with Paddy Power Games. One spin per player per day. Each prize carries individual T's and C's. Eligibility rules and T's and C's apply. 18 plus BeGamble.org.org.
Alright. Hi, Mystery. How you doing? Welcome on in. My name's Obi-Wan Pez. This is N Simplex Pachinko. We do math type stuff on Mondays and Wednesdays. We do gaming type stuff on usually Sunday, Tuesday, Friday. This week's a bit different because I took the last 2 days off because I've been sick. So you could probably still hear it. That's half normal. So as you rightly pointed out, yeah, proving it is a different issue. However, it's actually not too bad. So the extreme value theorem says that for all continuous intervals, there exists a minimum, a maximum, or both. Recently decided to dive into math as a hobby, coming from EE. Nice. So typically on Mondays we do like math education type stuff, and on Wednesdays we do more calculation-based type stuff. I'm still practically only just starting on the cracking the GRE math subject test. We're on page 51 of 380, essentially. And being somebody who took math in undergrad and also applied math in grad school, I never ended up taking topology, which is one of the classes that's covered in the GRE book. So I'm actually kind of looking forward to getting to the end of the book and doing that, because that'll be kind of the first time that I've had a look at it. If I don't understand something in here, I think my spouse has a topology book that I kept. Probably. It's probably down there somewhere. And if not, then I'll find one online, I'm sure. Okay, for all continuous intervals, continuous closed intervals, that actually does matter. So looking at this, we can say, okay, if we have, oh, no worries. If you have any like particular questions, feel free and ask, but otherwise, we always appreciate lurkers on Twitch. I believe a few of the streamers that I follow personally also say, like, you know, lurkers are the backbone of Twitch, because that's where a lot of people get their viewership. So, you know, I'm happy to be the voice in the background, as long as I don't annoy you too much. For all continuous closed intervals, there exists a minimum, maximum, or both. We could say this because in order to have a minimum, there are kind of two ways to go about it. So one is for an absolute minimum, we're looking at f at c for some c belonging to closed interval a to b. F of c must be less than or equal to f at x for all x on a to b. Closed. Again. It's because I was doing open intervals up there. Got confused. And for absolute maximum, again, the same type of thing occurs, where we have for all x in a to b, there exists a c on closed a to b such that f at c must be greater than or equal to all f of x. And we'll just reverse that, it's fine. All right, let's rearrange this argument. All right, and then relative minima are going to have something very similar. So here, we're going to say that there exists a c on our interval a to b such that, that's not just a comma, and there we go, such that and some some delta greater than 0 such that our f at c relative minimum is going to be less than or equal to all other f at c plus or minus delta. And same for relative maxima. We're going to be able to find some c value on that interval a to b where we can center a circle. Such that f at c will be greater than or equal to all other f at c plus or minus delta. Now, I'm also coming to the realization that maybe this is the end point. So we might just split it and say that, okay, it's going to be this or basically the same thing. Then we say that this one's going to be plus and this one's going to be minus. Wait, hang on. But we can't. But we can't only have it be one-sided. Haha. Where they exist. Okay, so asterisk, right? When f at c is an endpoint, the one-sided limit one-sided limit rule applies. So here we may only have one of those things exist. So C plus delta is not going to exist at B, and C minus delta is not going to exist at A. So we just don't have to worry about them specifically. Wow. So this says that for all continuous closed intervals, there's going to exist a minimum, a maximum, or both for every possible continuous closed interval. Should sound reasonable. Again, given the definition of minima and maxima, we're saying that for absolutes, there is no point that is higher than this point, or there is no point lower than this point. All of the points must be lower or equal to. All points must be higher or equal to for minimum. Okay. So then Roll says we can do this if f is continuous on a to b, then f of a equals f of b and is differentiable. So we could show that the slope, there must be some point between these values such that the slope is also 0, which is the same as the slope between the endpoints. Again, my half-assed explanation from earlier technically is sufficient for this sort of argument, where if we increased our value, we're going to need to decrease our value to get back to where we started. The thing that I was looking at here, this is geeksforgeeks.org. Right. So this gives us two possibilities. One, the function is constant, in which case, so proved. We don't have to worry about it. Case 2, if the function is not constant, then we do know that by the extreme value theorem, there must be a location where our function is reaching a minimum or a maximum or both, which is where f prime is equal to 0. So, has to be either at the endpoints or somewhere in between. If it's only at the endpoints, right, doesn't quite work that way. Because again, that's going to mean that, well, if it's constant slope or zero slope at the endpoints, then it's probably going to be constant slope elsewhere, and possibly the whole thing is a constant slope. Not the point. It must change its interval at least once on the inside of the interval. Again, safe to assume it has a minimum, maximum, or both by the extreme value theorem. And now we need to show that any of the interior points, the derivative is equal to 0. So, the derivative of the function is 0 at a minimum or maximum. Minimum or maximum. Since we already said there must be a minimum or maximum elsewhere in the function besides the endpoints, then there must be a minimum or maximum, or both. So at least one point somewhere in between f prime at those particular values must be 0. Righto. Then what Lagrange does is he says, okay, so let's start with a function f of x, which is the one that is the function that goes through our graph. Now let's assume that g of x is the secant line that runs through them. And now what's f of x minus g of x? We take that whole function and just lay it down on the x-axis because we subtracted g of x. And now it's also a function which now has its beginning and its endpoint at 0, which are equal, and so therefore it satisfies Rolle's theorem. So it really isn't difficult. It is a little bit of a pain to do it out in terms of rigorous algebraic mathematics, but it's okay. Not between. Right? So this is your typical mathematician deciding to do something that reduces a complex problem to something that's already been done. Since it satisfies Rolle's theorem, right? We wouldn't need to do a special proof by itself, as long as we get to this state and we've used a reasonable proof on Rolle's theorem. So yeah, this one, Joseph Louis Lagrange did this, what was then, or what is now called, the mean value theorem. Because this thing here is the average slope. Average slope of f of x on this interval a to b closed. Good evening and welcome to anybody who just came in or doesn't know who I am. My name is Obi-Wan Pez. This is N-Simplex Pachinko. We do mathy type stuff here on Mondays and Wednesdays usually. I took a couple of days off because I'm getting over something. And we do gamey type stuff on Sundays, Tuesdays, and Fridays, again, usually. If you're interested in any of that stuff, feel free to drop a follow or check out our YouTube. We also have many other math streamer friends who are coming online, usually sometime in the next couple hours. It being about 3 p.m. No, not 3 p.m. Jeez. Oh, man. Almost 7 p.m. On Eastern U.S. and 4 p.m. on Western U.S. So, some people are just about getting out of work and all that, so, or getting done with their evening activities. Right. So, mean value theorem. And then we said a while back here that this was going to help us find our minima and maxima All right, the sum of two non-negative numbers, x and y, is 12. So we know that x plus y is equal to 12. What is the largest product? So we have an objective function, which oftentimes we just call, like, you know, something, capital Z in this case. Z is going to be equal to x squared y. All right, we want to maximize our z-score on this, and we'd really like it if this was only in one variable. So, naturally speaking, we have here something that could be solved for y. Y, in this case, being a variable that doesn't have any extra stuff on it in the z function, makes it a lot easier to solve. And x is not any harder to solve for in the x plus y equals 12 function. So now we can plug all this into there. Z is going to be equal to x squared times 12 minus x. And now we want to take dz dx in order to figure out what the derivative function, the change function in z is. And then this will allow us to work out where minima and maxima are by setting it equal to 0. Okay, this is a product, so we use a product rule. X squared becomes 2x. We leave 12 minus x. Then we add x squared times 12 minus x, take its derivative, it's negative 1. So 0 is going to be equal to, here we can multiply this in. This is going to be a 24x minus 2x squared. And a minus x squared here. 0 is going to be equal to, right, 24x minus x, 3x squared. Here we could divide by 3, or just factor it out if we feel like it. Sure, why not factor out a 3x? That leaves us with 8 minus x. Okay. So the zeros for this function are going to be when 3x is equal to 0 or 8 minus x is equal to 0. Add x to both sides. This is x equals 8 or x equals 0. Now, this is not answering the question, but this is at least getting us somewhere. So we look at this and say, what do we get when we plug these numbers in? We could choose, we could take a second derivative and then figure out where the 0 is for that, figure out what the values are for the second derivative at 0 and 8, and see if that comes up with any sort of insight as far as like what curvature this has. Or we can look at this and say, okay, x being 0 is going to get us a product, right? Z equals x squared times y. X squared is 0. Doesn't even matter what y is, right? Y is actually 12 because, right, y equals 12 minus x, 12 minus 0. Okay. Z on the other side with 8 is going to be, this is 8 squared times, y is again 12 minus x, which is 8. So we get a 4 times 64 is 256. And z equals 0 on the other one. Now I do believe it said non-negative and not non-zero or whatever. Yeah. The sum of two non-negative numbers, x and y, is 12. So yeah. X and y in this particular case are going to be 0 and 12. And x and y in this particular case are going to be 8 and 4. What was the actual question? What's the largest product and smallest product of x squared and y? Yep. Good times. A rectangle in the fourth quadrant of the xy plane has adjacent sides on the coordinate axes. Okay, pretending that this is an actual rectangle. Oops. Sure, looks better. If the vertex opposite the origin is on the curve y equals log of x. Tell you what, let's go like this. Reform it. Ta-da! Nobody knows the difference. Shh. Nobody knows the difference. Shh. Alright, so y equals natural log of x. We've discussed this before. Anytime that this book makes mention of log of x, it actually means natural log. That is also pretty much what all coding languages do, or at least for the most part. If it just says log, it means natural log. Okay, what is the maximum area? So if we are maximizing this area, then our width is going to be just x. Our height is just going to be negative. Oh, hang on. That was silly. Right. So natural log does eventually go up and cross totally there. Ta-da. Totally there. Okay, so we've got x and the natural log of x. We want to know what the maximum area is for this thing. So, area is going to be the product of the two, x natural log x. We want to take then dA dx, so how much does the area change for every unit we change our x distance? This is a product again, so x, take the derivative, is just 1 times the natural log of x, plus x times, take the derivative of the natural log of x, and we get 1 over x dx. But again, dx is just 1. So dA dx is going to be equal to the natural log of x plus 1. Sorry, natural log of x plus 1. Careful with the intonations, right? Okay, now what we want is where is the derivative equal to 0? So natural log of x is going to be, nope, minus 1, nope, plus 1. Jeez. We're going to subtract 1 from either side. And where is the natural log of x going to be equal to a value of negative 1? Well, we could see it, right? A value of negative 1 for the natural log is going to be somewhere down here, wherever it's going to be. It hits every possible negative number on the way down. Right? From 0, way up here, at 1, 0, all the way back down toward x equals 0. So we're going to definitely have a point somewhere that satisfies this. And if you think about the area of the rectangle, right? as we get closer and closer and closer to 1 comma 0, it becomes much shorter and much longer. Eventually, the height runs to 0 because it's going to hit 1 comma 0, and the length is going to max out at a value of 1. So, again, area is going to be 0, length x is going to be 1. Alternatively, going the other way, as x gets really, really close to 0, our natural log gets really, really close to negative infinity. So that's an interesting one. That is an indeterminate value. So we don't know immediately what's going to happen there. If it goes off to an infinite area, well, that's really awesome. But we'll see it borne out in the mathematics when we get there. However, right? How do we undo natural logs? We got to raise e to those powers. And here we end up with x is equal to e to the negative 1. Yep. Okay, yep. So with area being x natural log x, we're going to get here that this is e to the negative first times natural log of e to the negative first, which is going to drop that negative 1 down front. We end up with a negative e to the negative first times natural log of e is just going to be 1. Now I will say right here, area, okay, sure, area should be technically absolute value and all that, but not the most important thing. It is in the 4th quadrant, so it will show up as negative. Whereas that doesn't necessarily prove it, we could also say, okay, we got this x value. What do? We could take the second derivative. So, second derivative of a with respect to x twice is going to end up taking natural log of x plus 1 and taking its derivative again. Natural log of x is just going to be 1 over x. And plus 1 is going to be 0. It's gone. And now we want to know, this is 1 over e to the negative first, which is just going to be e to the first. More importantly, right, this is just greater than 0. So if the curvature is, uh-oh. Yeah, uh-oh. Yep. All right. Right, okay. No, that was silly. Maximize the area. A must be the opposite of that, because we have to have a positive value for area. Alright, since natural log of x is less than 0 on x belonging to open 0 to 1. Oh, no, also open. Right, this is all going to be negative. That still reduces to the same stuff. That's going to be negative, negative, positive. There we go. Okay. Taking the second derivative, again, this is going to be a negative. Natural log of x is going to give us a negative 1 over x. Boy. It's going to be a negative e to the first, which is less than 0. So now it goes like this. Good. So if this has a downward trend, and we're at the point where it has a horizontal tangent line, then this ends up being a maximum. All right, so then our area is going to be equal to 1 over e. Alrighty. So, we'll be back next Wednesday with more GRE stuff, or any calculations if you're interested in finding something out. Typically, I will try to teach why stuff works, not just how it works. So it's going to also include some background, some possibly proof of whatever thing it is we're looking at, historical context, and then eventually, yeah, sure, the skill too. But for the most part, I do tend to like this other stuff as well, possibly, if not even more. So anyway, we have multiple math streamers who are usually on at least once a week. We got Zach at e to the 2i pi. We have Penn Center, who, nope, don't do that. Penn Center, who owns the Discord server that most of us use called The Elements. So if you go there, most of the time you can get a hold of one of us who might be interested in helping out in real time on Discord, all that good stuff. We also have Don Factorial, who is currently doing some DayZ type stuff. I guess he might not be on anymore, but been on for a while. I don't know. We have Dr. Gold at Actual Education, who generally does like math help, but also does physics and other cool stuff like that. He's been teaching out of UCLA? I think so. Or USC. Yeah, Southern California. He'd hate me for that. Oops. And I'm just gonna like completely forget the rest. There are many other people. If you go to that Discord server, you will be able to meet just about everybody. And head on in there, chat with whomever you like about mathy type stuff or otherwise. And again, we'll try to get you where you need to be. So let us go raid. Tonight, solar imaging with Third Rock Astronomy. We've also got Nerduino, who is a PhD astronomer, checking out some cool stuff, looking at telescope optics at the moment, it looks like. Give you an idea of who's around. Let's see, April Anonymous is somebody who does a lot of walking around New York City and hanging out and singing show tunes. So if you are interested in her type stuff, she is rather fun. Let's go check out Nerduino, who is doing NASA, or who has worked at NASA. Yes, that's right. And he'll possibly go check out Science streams. That's Belint, Lita, their daughter Ilona, and their newer son, Buster Brown. They do a lot of SciComm, cool stuff like that. We got Moo Hoodles, we got Volcano Doc, and we got Rocket Sage. Ian Stuckey, oops. 2 days in a row. Sorry, Stuckey. Anyway, we'll see you all possibly tomorrow for Against the Storm. Sunday for Satisfactory. Next Monday, we're doing more coverage of Peter Liljedahl's Building Thinking Classrooms, which is all about a sort of new teaching style that I've been working with for the past few years to try to really get it hammered in. And next Tuesday we've got 9 Souls, and Wednesday we've got more GRE. So have a good night, everybody. My name's Obi-Wan Pez. This is N Simplex Pachinko. See you later.